Recursion 2 split array. Given an array of ints, is it possible to divide the ints into two groups so that the sums of the two groups are the same? Every int must be in one group or the other. Write a recursive helper method that takes whatever argument you like, and make the initial call to your recursive helper from splitArray. No loops are needed. So let's go over the sample cases first. So the first case, we have the array 2, 2. Here, if we split the array into groups 2 and 2, they both have the sum 2, and therefore therefore we can split the array into two groups of equal sum, so we return true. Here we have 2, 3. No matter what we do, we cannot create two groups of equal sum. This is because the only two groups that are possible with this array is the case when one group has the element 2 and the other group has the element 3. Of course, both groups do not have equal sum, therefore we must return false. Here we have the case 5, 2, 3. So as is pretty obvious by looking at this case, if we split the array into a group consisting of only 5 and another group consisting of 2 and 3, these two groups, each element in this array are placed into a distinct group, and these two groups have equal sum, which is 5. Therefore, it is indeed possible, and we can return true. So then, how do we solve this recursively? So the key observation to make here is that one element, for example the element 5, can only be in group A or in group B. And this observation will help us split the array into a recursive tree. So here's what I mean. So for example, let's do the recursion on the group, so the sample case 5, 2, 3. So first we start with group A having nothing inside, group B having nothing inside, and then the array 5, 2, 3. We look at our first element. The first element is 5. 5 can either be placed in group A or in group B. If 5 is placed in group A, then group A with the addition of 5 would have the sum 5. On the other hand, B would still have nothing, and the sum for group B would be 0. The rest of the array is 2 and 3. Similarly here, if we place 5 into group B, then A will have nothing and will therefore have group sum 0, B will have 5, and the rest of the array is 2 and 3. So now let's do the next layer. So here we have the first element, which is 2. If 2 is placed in group A, then group A has a sum 7, which is 5 plus 2. B will also still have 0, because there's nothing inside B. The rest of the array is 3. Next, if we place 2 into B, then A will still have a sum B, but B will now have a sum of 2 because 2 was placed inside of that group. The rest of the group is 3. So next, similarly here, if we place 2 into group A, then A will have sum 2, B will be 5. The rest of the array is 3. Here, if we place 2 into group B, then A will still have 0, B will have sum 7, and the rest of the array is 3. Here, we do a check. So the only element, backtracking. So the first element is 3. 3 can be placed into group A or group B. If 3 is placed into group A, then, so if 3 is placed into group A, then A now has a sum 10, B has sum 0, and the rest of the array is nothing, because the array is now empty. Now we have the case where 3 is placed into B, so A equals 7, B equals 3, the rest of the array is null. In both of these cases, because A and B do not equal to each other, we know that the matching corresponding to these two base cases do not go along with the problem statement. Here we have 3, again as a first element. If 3 is placed into group A, then A has a sum 8 and B has a sum 2, the rest of the array is nothing. If 3 is placed into group B, then A equals 5, b equals 2 plus 3, which is 5, and the rest of the array is nothing. A and B are equal to each other. This entire path corresponds to a matching where we first placed 5 into group A, 2 into group B, and 3 into group B. This is how we reached this case. And because A equals B, we know that this is indeed possible, and we return true. As we noted before, the base case is the case when there is nothing in the array. If there is nothing in the array, we can do nothing to change the sums that we currently have. So all we can do is check if A equals B. If A does equal B, then we can return true. If not, we return false. So let's code this up. So first, let's write our recursive helper. So as noted here, we keeping track of three separate variables. So first, we keep track of I. I represents the place where we are at the array currently. Here, we just deleted the element from the array after we were done altogether. When we went from 5, 2, and 3 to 2 and 3, we just deleted 5. When we are actually doing the recursion, instead what we are going to do is to just keep a pointer at where we are currently. So if we have an array of all of these elements, we will just go from here, 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 and so on, all the way until we reach the end. In this manner, we will be we will be reducing the array and eventually be reaching a symbolic empty array. Next, we have the sum of group A and the sum of group B. We will also be carrying along with us the element array, nums. So let's first write our base case. Our base case is that when nums is empty, so when the length of nums equals 0, then we return if A equals B. If A does equal B, then we know that the corresponding pairing did work. If not, we return true because it did not work. Because the nums.length equals 0, there's nothing else we can do besides just check if the previous steps made it a ideal case. So next is a recursive step. So in the recursive step, we will be using bit operations to make this process easier. So what we know is that we can either assign the first element that I is pointing at into group A or group B. So if we place the element I into group A, then we will be moving on to the next element. We will be placing the ith element into B, so the sum of A will now be A plus nums I, and B would be untouched, nums would be untouched. Or, the other case is if we do the opposite. We still iterate across to the next element, so we increment I. However, we keep A with the same group, and instead we add element nums I to B. We of course leave nums untouched. In this manner, we will be recursively processing the array in this recursive approach. So now let's add our recursive helper function here. So we will return if our recursive helper function returns true. I of course starts at the first element, and because the array is indexed 0, the first element is 0. A and B will both have nothing because the groups are initially empty, and we will return the array. So let's see if this works. Logged out, I will quickly log back in. Yeah, so CodingBat does not like static. Oh, so one error that I made, that I forgot to do here, is that we were symbolically representing an empty array, or the rest of the array by iterating through with pointer I. So this is actually false. To those of you that caught it, good job. So the symbolic empty array is a case when our pointer is at is at an element that is not in the array. This means that I, the pointer I, is pointing at an element that is not in the array, which is I is greater than or equal to nums.length. So here's what I mean. If we have an array like this, like so, the length of the array is 4. It is indexed like so. All pointers following, so 4, 5, 6, etc., are pointing at elements not in the array. Therefore, whenever this is true, we know that we looked at the entire array, and therefore our array at our current state is empty. And so doing so, we get all correct.